All right, so this is 5.1. Doing 5.1 today. Probability rules. And so probability is the measure of the likelihood of a random phenomenon or chance behavior occurring.
Morning.
Hey, how's it going?
Good. I was just wrangling up my dogs outside. I was like, oh. So I've been going over instead of like doing, like emailing you and I guess us meeting on Zooms. I've kind of just been going back and watching the lecture videos.
Mhm.
And yeah, so that's helping a lot, honestly. With
Okay.
being, you know what I mean? Because the information is so, I guess, a different foreign language to me. You know what I mean? I just need to do it over and over. So I guess that's helping me. But
Okay. All right. Well, you know how to find me if you ever need anything.
yeah, I just figured let me not have him repeat everything he said and let me actually go back and watch the lesson. Like,
Right,
so
right.
that helps too. So thanks for recording them too.
Yeah, no problem. No problem. All right.
Okay,
So
last thing I'll say, y'all, but the Super Bowl. I got the, yeah.
that's all you got.
Uh,
I said, were you proud? Were you happy about it or no?
well, no, I was happy about that extra
Okay.
credit question because I got it right. I had no idea.
Oh, okay.
I don't know too much about football, so I was like, Tampa?
Yep, shot in the dark. Sometimes that'll do it. All right. So here we have the law of large numbers. And all it states is that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer and closer to the probability of the outcome. So in other words, the more you run an experiment, the more precise it'll be as far as the outcome is concerned. And that's all it's saying. It's the law of large numbers. Just run the experiment as many times as possible, because the more you run it, the more accurate your probabilities will be. All right. So an experiment is any process with uncertain results that can be repeated. So an example of that is flipping a coin. Your sample space will be the collection of all possible outcomes of an experiment. So in this case, when you're talking about flipping a coin, heads and tails will be your sample space. Those are all the possible outcomes of your sample space. So the sample space is denoted by S. So when you see S, capital S, in probability, we're talking about your sample space. Then your event is going to be any collection of outcomes from the sample space. So in other words, if I want to find the probability of landing tails, then my event would be landing tails. And that's normally denoted by any capital letter that you would like, of course, other than S, because S is your sample space. All right. All right. If I scroll up and you still copying, please let me know. All right. So the rules of probabilities. Like this. So we have P parentheses E, that's the probability of event E. Also, you see right here in red, the way you read that's P of E. Right there. I want to erase. So that's P of E. Your probability is going to be in between 0 and 1, inclusive. It can be equal to 0, and it also, or it could be equal to 1. So that's not out of the realm of possibility. We'll talk about what that means in a second. But your probability will never exceed 1 or be less than 0. Also, the sum of each one of the individual probabilities have to add up to give you 1. All right. So if it's a probability model, it must satisfy both rules 1 and 2. All right, so verify that this is a probability model. So we have this chart here that represents colors that could have been chosen out of, whatever, whether it be a bowl of red, yellow, blue M&Ms or something of that nature. But we have the color brown, yellow, red, blue, orange, and green. Then we have the probability of getting brown is 0.13, yellow 0.14, then we have 0.13, 0.24, 0.20, and 0.16. And we want to verify that this represents an actual probability model. Give me a chance to copy that before we go to it. All right. So rule one, each probability is in between 0 and 1. So that fits, each one of our probabilities. Nothing goes over 1, nothing is less than 0. Then rule two, if we were to add them all together, add up each one of the individual probabilities, they add up to 1. So if that wasn't the case, then it wouldn't fit rule two. So they need to all add up to 1. All right, so since the models satisfy rules 1 and 2, it is a probability model. All right, any questions on that?
Not right now, but I'm sure I will. I feel like this section is a lot of more vocabulary term based, right? Like definitions and stuff.
Yep, more so like conceptual versus this calculation. Yep.
Okay.
That's why I wanted to go ahead and knock this out, 5-1 out real quick. Well, I
Yeah.
don't say real quick, but today.
Yeah. Definitely.
So an event is impossible if the probability is 0. An event is a certainty if the probability is 1. The closer a probability is to 1, the more likely the event will occur. The closer a probability is to 0, the less likely the event will occur. All right, an unusual event is an event that has a low probability of occurring. Not messing anybody up with that top statement. Is that good? Okay. Nobody saying anything? Hopefully that's all right. Typically, an event with a probability less than 0.05, one of the worst 5%, is considered unusual. It is not set in stone, though. When you're doing your research or doing other things or go to another class, it may not be 5%, maybe a little higher, maybe a little lower. But for this class, that's what we will go with, that 5%. So hold on to that. It'll come up in another section or two wherein We're trying to find out if something is considered unusual, and we'll lean back on that 5% as our cutoff. So if something is less than 5%, it is considered unusual. All right. Calculating probabilities, the empirical approach. So the probability of event E is the frequency of E over the number of trials of the experiment. All right. An insurance agent currently insures 182 teenage drivers. Last year, 24 of them had to file a claim based on these students. What is the probability that a teenager, I said based on these results, I said based on these students, based on these results, what is the probability that a teenager will file a claim in a given year? So I'll let you write that first, and then we'll look at that. All right. So you would take the number of teens that filed and place it over the total number of teenage drivers that he have. That's 24 over the 182. And my math lab will let you know if they want it in a fraction or a decimal. I believe they wanted this one in a decimal, so that's why we got that 0.132 divided the 182 into the 24. Now, once you type in that value, or if they ask you for that value, you give it another way that they may ask for the answer. They may give you a statement, like maybe like 4 statements to choose from, to choose which one is the right one. So if you look at how this is written as an option, it says, so for every 100 teenage drivers, we expect about 13 to have to file a claim. So if you see something like for every 100, so what that means is that you're going to take that 100 and multiply it to your probability. So you multiply it to your probability, that gives you what, 13.2, which is about 13. So it will be based upon what options they give you. So if they said for every 1,000, you would multiply this by 1,000, and that means the number down there would be 132. So they would say for every 1,000 teenage drivers, we expect about 132 to have to file a claim. You know, so that's what we mean by that. So now, if it said for every 100, we expect 1.3 to file a claim. You know that would be the wrong statement, because when you multiply 100 to 0.132, you wouldn't get 1.3. You get that 13. So that's what I mean by that. When you see that number, you're going to take that number, multiply it times your probability, and that should be this number down here. Okay. So like I said, they'll probably give you 4 statements, and only one of them will be true according to, that process. right, questions on that? All right, problems before I scroll up. All right, so the classical method, very similar. Take the number of outcomes in E, place it over the number of outcomes in your sample space. Symbolism for that, in parentheses, E is N of E, just like we have P of E right here. And so that just represents the number of elements and or number of outcomes in E. The bottom one, number of outcomes in your sample space. All right, quick example of that. Going back to flipping our coins. We want to know what's the probability of landing tails. Flipping a coin and landing tails. So our sample space is heads and tails. So that means the number of outcomes in our sample space is just 2. What's the probability? We want to know the probability of landing tails. So that means our event is tails. Number of options or outcomes in our event is 1. Just tails. So once we have both of those, we place the 1 over the 2, and we have a 50% chance of landing tails.
I'm okay.
All right, sounds good. We have one more example. Nope, 2 examples. That would be good. But everybody good with this before I scroll up? All right. A single die is rolled. What is the probability of landing a number greater than 2? So our sample space, when we talk about a single die, if you play Monopoly, board game, or is rolling dice, throwing dice down, you have 6 options. So that's what I have right here, 1 through 6. And that means we have 6 outcomes. So I want to make sure we're clear that this 6 and this 6 have nothing to do with each other. So what I mean by that, if this was 1, 2, 3, 4, 5, 10, it still would be 6 outcomes. That could be 1, 2, 3, 4, 5 triangle. In other words, one side says triangle, the other one says 1 through 5. That still has nothing to do with the idea that that's still 6 outcomes. So you have 6 elements in there. So I just want to make sure that we don't think that, this 6 and that 6 have something to do with each other. In other words, since it ends in 6, then they'll put a 6 down there. No, it's about counting the number of outcomes that you have. Yep. Go back to my pen. All right. So then our event is a number greater than 2. So when you talk about how many options you have for your die, how many numbers are greater than 2? That's 3, 4, 5, 6. So we have 4 outcomes that are greater than 2. All right, place the 4 over the 6. And and simplify your fraction. That'll be your answer.
Do you always want answers in fractions, or is like a percentage also an acceptable answer?
My math lab will let you know.
Okay.
Yep, because sometimes they'll ask for the decimal and sometimes they want you to leave it in fraction form. Yeah, they'll let you know, and that'll be per problem, you know.
Okay, understood.
Great question, great question. All right. Anything else before we go to the next one? All right. So in this next one, we have a pair of dice instead of just a single die. We're going to compute the probability of rolling a 7, then compute the probability of rolling snake eyes, which is rolling a 2. All right. So just like with any probability, you want to establish your sample space first. Figure out what's the total number of all possible outcomes. All right. So when we look at, rolling 2 dice, you want all the possible outcomes. So you want the outcomes when die 1 is 1, die 2 is 1, die 1 is 1, die 2 is 2, die 1 is 1, die 2 is 3, and all the way down to when die 1 is 2, die 2 is 1, and 2, 2, 2, 3, 2, 4. So you want all possible combinations. So we're not going to want to have to list those out to figure out how many that would be, because it's easy to miss one if you're not careful. But bottom line is, according to the fundamental counting principle, die 1, if there's 6 options in die 1 and I can only choose one, 6 options in die 2, if I multiply those together, that will give me the total number of possible outcomes. So in this case, 6 times 6 would be 36. If it was die 1 had 6 faces, die 2 had 8, then you multiply 6 times 8, and that would be 48 possible outcomes. So you just multiply those two numbers together. However many total outcomes you have for each die, multiplying together, that'll give you the total number of possible outcomes. All right. Questions on our sample space before we go to the event? All right, our event is rolling a 7. So we can list out those options or those outcomes: 1, 6, 2, 5, 3, 4, and then 4, 3, 5, 2, 6, 1. So there are 6 outcomes in our event.
Sure, once I get into the homework, I'll probably have some questions.
Not a problem at all. So we take that 6, place it over to 36. That's our event over the sample space. And that's 1 out of 6. All right, so when it comes to snake eyes, there's only one way to get snake eyes. That's just 1, 1. Die 1 rolls 1, die 2 rolls 1 as well. It's the only way we can get 2. And we already established the sample space was 36. So that one's just 1 over 36. All right. Questions before we look at our last one for today. All right. So, where is this? Suppose a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. I'll give you a chance to write that piece before we scroll up. All right. A, estimate the probability of having 2 boys and 1 girl using the empirical rule. And then B, compute the probability of 2 boys and 1 girl using the classical method. All right. So let's look at A. Probability of doing having 2 boys and 1 girl, according to the empirical rule or empirical method, is that we would take 180, which was the number of families that told us that we had 2 boys and 1 girl, place it over 500 because there were 500 families altogether, and that gave us 0.36 as our answer. All right. So now to compute the probability of getting 2 boys and 1 girl using the classical method, first thing we can do is do a tree diagram wherein we examine all possible ways you can get 2 boys and 1 girl. So if your firstborn is a boy, starting here, firstborn is a boy, then there are 2 possible ways you can go with that. The next born could be a boy or it could be a girl. And then for your third, there are 2 possible ways of establishing that, or 2 possible ways it could go. And of course, that's being a boy or girl, and then from the girl being a boy or girl. So you just do that tree for each scenario. And then you do the same thing, starting off with a girl first, and then do boy, girl, and then from each one of those, do boy, girl. And what that does is it gives us 2, I said 2, gives us 8 possible outcomes altogether. So that's our sample space. You count each one on 1, 2, 3, 4, 5, 6, 7, 8. You have 8 possible outcomes altogether. And then as far as our event of 2 boys and 1 girl, you see right here we have 3 different scenarios that fit that description of 2 boys and 1 girl. The order doesn't matter. The scenario is what we're looking for, having 2 boys and 1 girl. So before we finish off the problem, questions on what I did, how I set it up, how I got my answers. All right, so now we place the 3 over the 8, and that'll be 0.375. Questions on anything?
Nope.
So that's it for 5-1. As with anything, try the stuff out, see if you get stuck, or ask questions. We do have a question that's on the floor, so we'll take care of that. Let me go to a review page. All right, so I forgot who it was that asked me that question. We were talking about the least squares regression line, though. So which number was it that you were looking at?
Like the question?
Yeah,
It was just like I was just trying to get through any of them, and I was like, I don't think that I'm like solid on the process yet. So
Well, see, that's
question.
why I need to make sure, because remember, now were you okay with going to a website and just using easycalculation.com or something of that nature?
Oh, yes, I did. Okay, yeah. Okay. I'll
Oh, so you forgot about that?
I did forget about
Okay.
I
Well,
think that's one of the steps I was missing. I was like, I don't calculate this.
okay, yeah, okay. So try it out, and
Okay.
then so just remember this. Let me do this real quick.
You said it's called Easy. Okay, I really
Yeah,
did
I'm
forget
about
that.
to go to it now. So I would go search. I would do let's say regression line, easy calculation. And then the first one should be it right there.
Okay, thank you.
Not a problem. And so then you pop it up, you can type in the X value, Y value. So yep. I think that was the problem that I gave you, that we did that. They gave you a data set and you would type in the data set. But if you try it out, if you go there and it's still not fitting what what I said, then just bring the question back and then we'll figure it out. But
Okay, thank
I
you.
think that's what that is pertaining to. We use that. All right. Anybody else? Everybody good before we close out for today? Trying to get this.
Once I get into the homework, definitely. But I'm gonna rewatch the lesson as well if I do miss anything. You know what I mean? Before I go out and message you so we can meet up individually and stuff.
Mm-hmm.
So yeah.
Okay. Sounds good to me. Sounds good.
Yeah.
So,
I appreciate your time.
not a problem. Appreciate you guys coming through. I will see you on next class. Be safe and take care.
Yes, definitely. Thank you so much.
Thank you.
Thank you. Y'all take
You
care.
guys have a good day.